Somewhere in a distant patch of sky, James Webb photographed a galaxy so far away that its light left home when the universe was less than 300 million years old, barely 2% of the age you were taught in school. That part isn't controversial. What's controversial is what astronomers found when they actually looked closely at that galaxy's light. Instead of a young, chaotic, barely assembled smear of newborn stars, the kind of thing every model predicted they'd find at that distance, they found something that looked, in places, disturbingly mature. Fully formed structure, signs of stars that had already been burning for tens, possibly hundreds of millions of years, in a universe that, at the moment that light was emitted, hadn't even existed for that long itself. That contradiction has a name among astronomers now, only half-jokingly, the impossible early galaxy problem. And it's only one half of a much bigger, much stranger story currently unfolding around the single number every physics class in the world takes for granted, the age of the universe itself. Let's start with the discovery that actually created this problem, because the scale of it is worth sitting with properly. James Webb Space Telescope was built with one of its central missions being exactly this: peer as far back into cosmic history as physically possible, capturing light that's been traveling toward us since almost the very beginning of everything. Within its first year of operation, it began finding galaxy candidates at extreme distances that kept getting pushed further and further as astronomers refined their observations. The current record holder, a galaxy called MOEM Z14, was confirmed in a 2026 paper by researcher Rohan Naidu and colleagues, publishing in the Open Journal of Astrophysics, to sit at a spectroscopic redshift of 14.44. In plain terms, that means the light Webb captured left that galaxy when the entire universe was less than 300 million years old. An earlier record holder, a galaxy called JWST Z14-0, gives an even clearer illustration of exactly why this became such a genuine puzzle rather than simply an impressive distance record. A detailed 2025 study, published in Nature Astronomy, used Webb's mid-infrared instrument to get a much better look at that galaxy's actual visible light, rather than just its most distant, most redshifted signal. What that analysis found was a preferred model containing roughly 500 million solar masses of stars, built up through what looked like an extended, ongoing burst of star formation. Some of the modeling allowed for star formation stretching back roughly 100 million years before the light being observed was actually emitted. Sit with that specific number for a second. 100 million years is a genuinely long stretch of continuous stellar development to have already unfolded, inside a universe that, at the exact moment that galaxy's light left it, had only existed for a few hundred million years in total. It's not mathematically impossible under the standard model, but it sits right up against the edge of what the model comfortably allows, tight enough that a small number of researchers started asking a much more radical question. What if the problem isn't with these galaxies at all? What if the problem is with how old we think the universe actually is? That question led to one of the more startling proposals to come out of cosmology in recent years. Physicist Rajendra Gupta developed a model combining a modified version of an old theoretical idea called tired light with something called covariant coupling constants, essentially a framework that reworks some of the basic assumptions behind how we calculate cosmic time. Run through that model, the age of the universe comes out to roughly 26.7 billion years, nearly double the conventional figure most of us grew up learning. Under that kind of framework, those unsettlingly mature-looking early galaxies stop being a paradox entirely, because there simply would have been far more actual cosmic time available for stars within them to form, age, and accumulate mass before their light ever reached Webb's mirrors. It's genuinely important to be precise about where an idea like this actually sits, because it would be dishonest to present it as anything close to settled science, or even as the leading competing view among working cosmologists. It's one specific minority proposal, put forward as one possible way to resolve a real, still unsolved puzzle, sitting alongside several other, less radical explanations that stay entirely within the standard cosmological framework. Some researchers have proposed that the earliest galaxies may simply have converted gas into stars far more efficiently than current models assume, allowing them to build up mass more quickly without needing any change to the universe's overall age. Others have pointed toward the possibility that unusually large, rapidly growing black holes at the centers of these early galaxies could be adding extra brightness to the signal Webb is capturing, making the galaxies look more massive and more mature than they actually are. As of the middle of 2026, the overwhelming majority of professional cosmologists continue working within the standard 13.8 billion year framework, treating the early galaxy puzzle as a genuine active challenge to be resolved inside that model, not as proof the entire model needs to be thrown out. But here's what makes this a genuinely two-sided story, rather than a single one-off controversy. While one small group of researchers has been quietly proposing a much older universe to explain unusually mature early galaxies, an entirely separate, Much larger and considerably more mainstream body of cosmologists has spent the same stretch of years wrestling with a completely different tension, one that, if it's ever fully resolved, points in the opposite direction entirely, toward a slightly younger universe, not an older one. That second tension is called the Hubble tension, and it comes down to a genuine, persistent disagreement between two independent ways of measuring how fast the universe is currently expanding. One method uses the cosmic microwave background, the ancient afterglow radiation left over from the Big Bang, mapped in extraordinary detail by the European Space Agency's Planck satellite, which produces an expansion rate of about 67.4 kilometers per second per megaparsec. The other method measures the distances and velocities of relatively nearby galaxies directly, using specific categories of stars as reliable cosmic yardsticks, and consistently produces a noticeably higher number, somewhere around 73. For years, many cosmologists assumed Webb would eventually resolve this disagreement, most likely by revealing some subtle measurement error in the local nearby galaxy method, since crowded star fields and interstellar dust could plausibly be throwing off those specific calculations. Instead, when astrophysicist Dan Skolnick and his team specifically tested that possibility using Webb's vastly superior resolution, they found the local measurements held up. Webb closed off what had been considered the most likely, most mundane explanation for the discrepancy. At the January 2025 American Astronomical Society meeting, Skolnick described the resulting situation plainly as a crisis for the field. Then, in December of 2025, an entirely separate, independent measurement technique added even more weight to the puzzle. Researchers studying the subtle time delays in light from gravitationally lensed quasars, extremely bright, distant galactic cores whose light gets split into multiple images by the gravity of a foreground galaxy, found results siding with a faster local expansion rate, rather than the older cosmic microwave background figure. As of 2025, the overall disagreement between these two competing measurements had reached a statistical confidence level exceeding 6 sigma, a threshold high enough that ordinary measurement error becomes an increasingly implausible explanation on its own. Here's the detail that makes this whole story genuinely fascinating rather than simply confusing. If that faster, more locally measured expansion rate eventually turns out to be the correct one, the most direct mathematical consequence, worked through the standard cosmological model, wouldn't be an older universe at all. It would very likely be a slightly younger one, with revised estimates shifting the age down toward somewhere between 12.5 and 13 billion years, rather than up toward anything close to 26 billion. A universe expanding faster today generally implies it reached its current size more quickly, which, worked backward through the equations, tends to mean less total elapsed time since the Big Bang, not more. So here's where that leaves things, and it's worth being completely honest about the state of play, rather than picking whichever version makes for the more dramatic headline. Two genuinely separate scientific puzzles are currently unfolding around the age of the universe, and Webb's remarkable data sits directly at the center of both of them. One puzzle, involving strangely mature early galaxies, has led a small minority of researchers to propose the universe could be nearly twice as old as commonly believed. The other, involving a persistent, deepening disagreement over the universe's current expansion rate, points, if anything, in the opposite direction, toward the universe potentially being slightly younger. Neither puzzle has been fully resolved. Neither has produced a new number that has actually replaced 13.8 billion years within mainstream cosmology as of today. What both of them genuinely have done is make working cosmologists considerably less confident and considerably more publicly candid about how solid that familiar number actually is. That's the real story behind the headline. Not a quiet, already completed correction slipping past public notice, and not a single dramatic reveal captured in one telescope image. Something messier, and honestly more interesting. One of the most fundamental numbers in all of physics, treated for a generation as essentially settled, currently sitting at the center of two separate, serious, still unresolved scientific arguments, both traceable directly back to data captured by the same telescope, pointing, frustratingly, in two different directions at once. If stories like this, the ones where real unresolved scientific uncertainty turns out to be more compelling than any tidy, finished answer, are what you come here for, stay close, because this particular question is far from finished being asked.